Hello everybody, my name is Philip Johnson and today I'm going to discuss an experiment I conducted concerning an object in motion with constant velocity and iterative motion prediction using Newton's second law. We'll discuss, in order, assumptions for the experiment such as participants in the model, choice of axes and time scale, motion observed in the experiment, the computational model of the experiment and its use of Newton's second law, and the comparison between the experiment and computational model. The object I selected for the experiment was a tennis ball. This tennis ball was rolled from left to right across a coffee table in my house. The choice of the tennis ball and location for the experiment was easy. It was what I had readily available to experiment with. To collect my data, I used my dumb phone and an iterative method in the tracker software. I selected the center of mass of the ball frame by frame in a selection of frames that I deemed the ball appeared to be moving at a constant velocity. It was my choice to have the axes start at the center of the ball in the first frame of constant velocity motion, and to line the axes such that the ball is moving predominantly in the positive x direction. The choice of axes was just to make the data pleasing to my eye. We could have had the ball move along the negative x, the positive y, the negative y. The data would have been the same, minus, plus, and negative signs, and if I had decided to have the ball move through the y-axis, then the data would have been in the y column shown here. The point is the ball is experiencing the same forces and performing the same motion regardless of axis choice. The concept being there's no defined protocol for what is x and what is y. As experimenters and scientists, we make the decisions on axes. This time, I decided on positive x. It is also worth noting that I chose the minimum time scale between data collection points as allowed by my camera. My camera records in 30 frames per second, so 0.033 seconds elapse between each data collection point. Now we've discussed the assumptions for our experiment, let's move on to motions observed in the experiment. A quick view of the video sees the ball move in the positive x direction and also a tad to the negative y direction. This is human error. The ball was meant to be thrown directly straight, but the ball sort of veered off to the thrower's right. Since our computational model will use Newton's second law to predict movement, we can already predict some inconsistency between the model and the experiment. Why is that? Here's some quick math involving the initial positions of the tennis ball and the second data point collected. I derived a velocity of about 1 meters per second in the x direction. This does not account for any kind of y movement, the kind of y movement that we see in the video at later points in the ball's movement. As such, we can expect a little discrepancy between the experiment data and the model, because the model is given only a x direction for velocity. Let's move on to the computational model of the experiment, now that we've already seen the motion observed in the experiment. The following is Newton's second law in an equation. With minor algebraic manipulation, we can maneuver Newton's second law to generate an equation for the final velocity of an object. This is interesting because we can predict the velocity of an object just giving an initial velocity, mass, time, and net force. Net force that we're assuming to be 0 for this experiment. Similarly, we have a position equation that has similar parameters that we also can give to the code. This will allow our computational model to predict the motion and position of our tennis ball. We'd have to do this over and over by hand, but we have a computer. Here's the salient parts of the while loop and the data that we gave the code such that we can predict the motion of our ball. The computational model that results is very similar to our actual data. I wonder what the differences are. All that being said, graphing the actual data from our experiment and using our computational model, we see some discrepancy. Why is that? Foremost, the whole assumption of our experiment is that the ball is moving at constant velocity, 0 net force. That's why we didn't have to give net force to our code. We just assumed it was 0. Calculating the various pushes and pulls operating on the ball is an extremely daunting task. There's friction from the table, possible air resistance, so much more that we can hardly imagine to calculate. The net force was not 0 in the real world. Furthermore, there was some human error in the experiment. The ball didn't just move in the positive x direction, it moved towards the camera. That being said, there still were some data points where the experiment and the model connected. But over time, as the factors such as friction and air resistance factored in, we see pretty huge discrepancy by the end of the ball's roll. Thus concludes my analysis of my constant velocity tennis ball. Feel free to comment in the YouTube comments below. Or don't. Grade nicely. See ya.